Welcome to lecture number 20. In this lecture, we are going to do quantum measurement. Measurement is a very important aspect of quantum mechanics and quantum information. And in this lecture, we will try to do measurement in with mathematical details, as well as we'll try to have some intuitive understanding about the measurement. And what we do for these measurement will also then we will also then see how this measurement actually manifests in the context of two photon detection as well. So before we get started, let's look at what we did in lecture number 19. So in lecture number 19, we derived the general two photon state, including the frequencies and the special frequencies, so that this state is applicable not only for the temporal two photon interference but also for the spatial two photon interference effect. So this is the general two photon state that we derived in the last lecture, and we looked at the two special cases of this. One is when the signal idler directions are fixed, that means QS and QI when they take only when they each take only one value, that means the photons go in particular direction. In that case, the two photon state can be written like this, Sn double integral over frequencies. We also look at the other case where signal idler fields are monochromatic, and in that case the two photon state is written as integrals over Qs and Qi. That is the transverse wave vectors of signal idler. This is the two photon state that is relevant when we study spatial two photon interference effect, and that's the two photon state which is relevant when we study the temporal two photon interference effect. We then also looked at the generic two photon interference, and we considered this setup. In this setup, we are producing two photon state using partially coherent pump, and the down converted photons can now reach these detectors in two different alternative ways. In the alternative one, the two photons are going through these holes located at rho S1, rho I1, and in the other alternative, the two photons are going and reaching the detector through the holes at rho S2 and rho I2. So these are the two alternative ways in which the down converted photons can reach the detector and get detected in coincidence. So two photon interference happens if these two alternatives are indistinguishable, or if these two alternatives are coherent with respect to each other. And then in order to derive the conditions for coherence, we then constructed these quantities delta rho and delta rho prime and defined it in them in this manner. And these definitions for delta rho and delta rho prime in this spatial domain is pretty much the same as we define delta L and delta L prime in the context of temporal interference. We now in this in terms of these quantities and assuming the pump to be a partially coherent field, we then derived the coincidence count rate at this detector, and we found that this has this kind of expression. The first term is essentially the coincidence count rate if only alternative 1 was there, 1 was allowed. The second term is the coincidence count rate when only alternative 2 is allowed, and the third and fourth are the cross terms when both these alternatives are there and when they can interfere with each other. This quantity, this W2, this we call the two photon cross spectral densities, and this S2 rho S1 rho I1, this we call the spectral two photon spectral density in alternative 1, and this is the two photon spectral density in alternative 2. And this mu2 we define as the that shows up here, we define as the degree of spatial two photon coherence. So we see that the structure of interference in terms of coincidence count rate is pretty much the same as we have seen in the case of classical one photon and even two photon temporal, and that is that you have the first term from alternative 1, then the second term from alternative 2, and if the two alternatives can interfere, then we have these two cross terms, and the degree of coherence between these two alternatives is quantified through this quantity mu2, which is called the degree of spatial two photon coherence. So very similar structure of interference we are seeing here in this two photon interference. And again, in the quantum language and in the sense of what Dirac had said, we could see that here also we can see two photon interference as a two photon interfering with itself. So we still have two photon, but it can be either in this alternative or in that alternative, and in that sense we can say that it's a two photon interfering with itself. Okay, so this is what we did in lecture number 19. So in this lecture we want to study quantum measurement. Now, measurement in quantum mechanics is basically an act to obtain some information about the quantum state. A quantum state in quantum is usually a black box, and until we act on it with some operator, we do not obtain any information. So in order to obtain some information, we have to act on the quantum state using some operator. For example, here we have a field like a quantum state of this field going through this double slit. So there is a quantum state of the photon or particles right here, and then we want to know as to where this photon will land on the screen, and this we can obtain, this information we can obtain if we act a position operator on the state, or if we do the position measurement. So if we measure the position, what do we obtain? So we know that an act of measurement collapses the system into one of its eigenstates. So of course, if we do make a measurement, we'll find that this photon or this particle is somewhere on the screen. But where on the screen, or which particular eigenstate x, that is completely unknown, and that it is actually impossible, even in principle, to predict what the state of the system, what state the system will collapse into after the measurement. So this simply cannot be predicted. So that's the generic understanding of measurement in quantum mechanics, and in this lecture we'll try to have the mathematical formalism to represent this generic understanding, and as well as we'll try to provide some intuitive way of understanding these concepts. So in general, there are three different types of measurements that are discussed in the context of quantum mechanics, quantum information. These measurements are, first one is general quantum measurement, second is projective quantum measurement, and then third is positive operator valued measurement. That's called POVM. I mean, this projective measurement is basically a special case of this general quantum measurement, but this projective measurement is typically what we do within typically what we study in the courses is basically the projective measurement, and in this lecture and in this course we will also be concentrating only on the projective measurement. But in general, there are these three different types of quantum measurement that actually definitely are discussed in quantum mechanics, quantum information. Okay, so what are these projective measurements? So let's say A is a measurement operator that is in a Hermitian operator corresponding to an observable. So we have A as an Hermitian operator. Of course, it corresponds to a dynamical observable. So now we know that if the quantum system psi is in one of the eigenstates of this Hermitian operator, then the system remains unchanged when measured by the operator A. That is, if psi is equal to AI, this ket AI, where this ket AIs are the eigenstates of A, then if we act on this state with this measurement operator A, the system remains the same, it doesn't change. And AI are of course the eigenvector corresponding to this operator A, and AI are the eigenvalues. Of course, if you have another measurement operator B corresponding to some other dynamical observable, then of course B will have its own set of eigenvectors and eigenvalue. And in that case, only if the quantum system is in one of the eigenstates psi equal to BI's are the eigenstates of B, then only the system remains unchanged when measured by operator B. So for a quantum system there can be several dynamical observable, and a system remains unchanged only if that system is in one of the eigenkets corresponding to the operator that it is being operated on by. But now let's say in general, if the system is in a superposition state, for example, if we write this state in terms of the eigenkit of the measurement operator A. So we can write it like this, that psi is like sum of AI, where the coefficients are alpha I. So this can be written like this. So that's the superposition state. We can also write it like this, where we are writing this alphas as AI psi. So that's the projection of psi onto these eigenkits. This should be A1. This is the state representation in the AI basis, or in the eigenbasis of the measurement operator A. So of course this is a superposition state. This is not a single eigenkit. So that's a superposition state, and the way we interpret this kind of state is that this quantum system exists in all these basis states AI simultaneously. But upon measurement, of course, we will find this to be in one of the eigenkits, either A1, this should be A1, that should be A2, and this should also be A1. Okay, so when this is a superposition state, the quantum state exists in all these basis states AI simultaneously. And when we do the measurement, of course, the system then collapses into one of the eigenkits, A1, A2, or AN. And the probability of finding the system in a certain basis state is AI psi square, and this we get through this state representation. This we already know. Now, so what happens if the measurement operator A acts on this state, which is not an eigenkit but a superposition state? So what happens here? Okay, so that's the state and that's the measurement operator. Now the exact state, of course we know the system will collapse, but the exact state in which the system collapses upon this measurement, that cannot be predicted even in principle. Of course, a given measurement collapses the system into one of its eigenstate and yields the eigenvalue. And the intrinsic uncertainty associated with superposition is same as that associated with the measurement. What I mean is I mean, we write the state as a superposition. So here we say that the quantum state exists in all these basis states simultaneously. This is just a statement of the fact that there is no way of knowing which state, which AI the quantum state is in, and that is what we mean by saying that it exists simultaneously in all these basis states. And upon measurement, then we find that it is just one of the state. So that intrinsic uncertainty that we see with the measurement is the same that we have in here as in the case of superposition. Okay, so now if we act this measurement operator on the state, the system sometimes collapses into this state A1 and gives out a value, the eigenvalue A1, and the probability that this collapse actually happens is A1 psi squared. That is the projection, and that this is the same probability that we get as to what should be what would be the state in this superposition. Now, maybe on second measurement we find that the system collapses into A2, and this time if it collapses into A2 we get the eigenvalue A2, and the probability of this collapse happening would be PA2. So that is A2 psi mod square. And of course it can also collapse in AN, I mean any of the given state with the eigenvalue AN and so on. So a measurement, even though it's a superposition state, it will collapse it into one of these state, but this is for a single measurement. And these values of the probabilities, we can only obtain these values only after doing a lot of measurement, and then that will allow us to get these values. But a single measurement will collapse the system into either A1, A2, or and one of these eigenstate. Okay, now the probability, the PAI, that a measurement of the observable yields the result AI, let's write it in this manner. So this should be PAI. This we can write as AI psi square, and of course we can let's write this as AI psi dagger. Since this is a complex, these two are complex number, we can switch them. So write it like this, and then AI psi, this we can write as then psi AI. So now we can write this PAI rather as the psi AI ai psi. So this we call as the projection operator. This ai, this we call as a projection operator, that we are representing by this pi I. That is the projection operator. Why is this a projection operator? That we can see. Let's do the action of this projection operator on the state. So let's act with this pi I on the psi. So we have this ai acting on the psi. With psi we are writing as alpha j aj. Now this ai that we bring inside, alpha j is here, so that ai comes in here. We have this ai aj. This since these are orthogonal states, eigenkets, then that gives us a delta function, and we have alpha I ai. So this projector pi I acting on psi basically yields this state ai. So the projection operator is basically projects and collapses the system into one of the eigenstates. So that's what it means. So that's why we call it a projection operator. So that's the projection operator corresponding to the operator A, and there will be n such operator if the dimensionality of that operator is n. Okay, so what we have seen so far is that a single measurement by a Hermitian measurement operator collapses the system into one of its eigenstates. Which particular eigenstate or eigenket the system collapses into, or which particular projection operator does the action, that cannot be predicted. What we can have is just the probability, but in order to actually get these probabilities pai for getting the eigenket ai, this experimentally can only be obtained by doing a very large number of individual measurements. In one measurement the system just collapses, one cannot find this probability, but in order to get this probability one needs to do a large number of measurements. Of course theoretically we can calculate it if we know the state. But quite often in experiments the aim is to do the state reconstruction, which one doesn't know the state, and in which these probabilities are actually calculated by doing a large number of individual measurements. Okay, so this is what we have seen so far. Now we also realize that in this measurement the total probability of the measurement has to equal to 1. So that means pai sum over all the states, that has to equal to 1. So pai we can write as ai psi mod square, and this then we can write as ai psi, and then since this is a complex number we can write it like this. Ai psi dagger we can write as psi ai, and since we have if we have the state as normalized, then of course we get from here that ai that is equal to 1. So this is essentially a completeness relation, which says that the sum of all these projections has to equal to 1, and this means that when we do the measurement one of the projectors has to become active and the system has to be found in one of the eigenkets. So that's what it means. So that's the completeness relation we get from the fact that the total probability of measurement has to be equal to 1. Now we can write this action of this measurement operator. Now let's write it explicitly. This A acting on psi. So this is A psi. We can we write in the eigenket ai in this manner. So now we can bring this A inside here. This is just a number. So this A acting on ai gives ai, and that's the eigenvalue, and in the expanded form it looks like this. So this is what the A operating on psi, operating on the state makes the state. So that's the state after A has kind of acted on it. But when we have the when we associate the meaning of measurement with this operator A, of course A acting on psi gives just one of the eigenket, but symbolically we can write it like this. So this is just a superposition state, and of course it represents all the possibilities associated with measurement by A, and this kind of expression is definitely useful in calculating the expectation values, because in calculating the expectation values we take ensemble average over all possible outcomes that can there be. So now again this A acting on psi, we can just write this quantity over here. We can just rewrite this as in this manner. This is just a number, so we are writing, bringing it here, and so we write it in this manner. So this A psi is like this. So this basically implies that this quantity AI Ket-Brach AI, this is just operator A. So that is the operator, this is the representation of A in terms of these projectors. So and that's the eigenvalue associated with AI. So that's the representation in terms of projector. Also, if we have the two different projectors are actually orthogonal, we can see that like this. So this is pi I pi j. So AI aj aj. Since AI aj are orthogonal, we get a delta function here, and so that's the orthogonality relation. So different projectors are orthogonal to each other. Okay, now finally the state after measurement, that's the state after post measurement, that we can write like this. So that's pi I acting on psi, and then this is being normalized by the probability of obtaining the state I. Of course, pi I acting on psi so that's the projector pi I acts on psi. That gives us this AI we write like this, that's AI psi divided by this quantity which is AI psi mod square. So this is essentially AI except for a phase factor. So of course the state after measurement has to be AI, but this is how we actually represent it. So now that a particular measurement yields just one of the eigenvalue or one of the eigenket, particular measurements are not very useful. So in quantum information, quantum mechanics, we mostly talk about the expectation value. That is the value of the measurement variable expected after a lot of measurements. So the way we define expectation value, this we have done earlier as well, but now we'll do it in the context of this measurement. So the expectation value of A is written like this, and that is the eigenvalue times the probability of getting that particular eigenvalue. This we write as AI psi mod square, expand it like this, then we can swap it like that. Again write it, just get rid of this dagger by and then this is essentially this, and here we have just used the fact that this sum over AI that is equal to 1, and that is actually the operator A. So the expectation value of A on any operator is basically the psi A psi, this quantity, but experimentally when we calculate this quantity, this involves actually a large number of measurement, but that's how we actually theoretically write it. Okay, so far we have done the measurement with discrete variables, but measurements can also be with continuous variable operators such as position, momentum, and so we'll just do this measurement in the position basis. I mean the formalism is exactly the same as what we have done for the discrete. Only thing is that wherever we have this summation, that will be replaced by integrals. But so let's just go through it really quickly. So state psi in the position basis we can write as psi x and x ket, like in this manner, where the psi x can be written as x psi, and we know that the probability that a measurement of a position collapses the system into eigenstates between x and x plus dx is psi x square dx. So psi x square is the probability density. So since this is a continuous variable, we'll talk about we talk in terms of probability density instead of probabilities. And if you want to calculate the probability, then we multiply it with dx and then integrate over the range of variable that we are interested in. Okay, so what happens when this position operator acts on the state psi? Of course, this measurement collapses the system into one of the eigenstate, this x with eigenvalue x, and the probability, the associated probability density here is psi x square. Now the projector in this case is we can write as pi x, that's just xx, and the action of this projector on the state psi, we can see this xx acting on psi, we write this psi in this manner. Then we bring this x inside, and this thing gives us a delta function, delta x minus x prime delta, and so this projector acting on psi essentially then gives us this x. Of course, we need to normalize it with respect to this psi x. So xx projector acting on psi gives us this eigenstate x. So that's what this projector actually means. Now similarly we can have the completeness relation here, and that also comes from the fact that the total probability of obtaining the state at some x has to equal to 1. So this px dx from negative infinity to infinity, that has to equal to 1. This px is essentially the probability density, which is the psi x square. So that has to equal to 1. Psi x square we can write like that. And then this basically says that the xx dx integrated over all space, that has to equal to 1. So that is the completeness relation we have over here. So that's a projector, and if we take all these projectors, then they have to integrate up to 1, because the particle or the system has to get observed somewhere in x. Okay, now we can write again the action of the operator x on psi, and that we write as x psi x x dx. We can bring this x inside because that's just a function, and this x acting on x, the operator x acting on this ket, just keeps this, since this is an eigenket, so it remains as is, and we get this eigenvalue out. And so we can essentially basically then write this, we can see this, push this psi over there and rewrite it, and essentially what we get is this x operator has this kind of representation. Again, this is exactly the same that the thing that we obtained for the discrete case. So that's the representation of this continuous variable position operator in terms of these position projectors. Okay, I mean this formalism is pretty much the same for the continuous variable as we had for the discrete. So no surprises here. Okay, so now when we talk about quantum measurement in a given basis, so a quantum measurement or in a given basis is always associated with a measurement device, which is used in order to experimentally reconstruct the state when we don't know the state. So for example, if we are working in the horizontal vertical polarization basis, if we are doing the measurement in the horizontal vertical basis, the measurement device is a beam splitter that splits a field based on whether it is horizontally polarized or vertically polarized. I know Z here. So beam splitter, this is a polarizing beam splitter in the horizontal vertical basis, and the way it works is that if you have a vertically polarized photon coming in, it will send it this way, and if there is a horizontally polarized photon coming in, then it will send it that way. So this is this polarizing beam splitter is acting as these two projectors, and since polarization basis is a two-dimensional basis, we have only two projectors and making these photons go in these two different directions. Of course, we can't have any situation where we have one photon here and one photon there as well. So it has to be either the photon has to get detected either with the vertical projector or the horizontal projector. Now one can also have even in the -45 polarization basis, and in that case the measurement device would be a beam splitter that splits a field based on whether it is 45 degree polarized or -45 degree polarized. For position basis, the measurement device could be a CCD camera with each pixel acting as a position location. In a momentum basis, the measurement device can actually be a lens along with the CCD kept at its the focal plane of the lens. So measurement in any given basis is always associated with a measurement device. Sometimes the device is easily available, sometimes that device need not be easily available or maybe still a part of the emerging technology, but there always has to be a measurement device associated with the measurement in a given basis. Okay, so when we talk about quantum measurement, the main aim of the quantum measurement is to do the state reconstruction. So typically the state that we have, the quantum state, we don't know what the state is, and the aim is to find out that state or reconstruct that state, and that state reconstruction happens through quantum measurement. So when the system is, if we know that the system is in one of the eigen states, then only one measurement is needed to guess or reconstruct the state. So we can take one example here. So suppose if we know that the state, the system is in this vertical polarization, and of course we know this horizontal vertical is a two-dimensional basis. So here, if we know that the system is in one of the eigenkets and it is let's say V, and if we bring in this measurement device polarizing beam splitter in the horizontal vertical basis, now then for this device, if we make a measurement, we will find that the photon, in the first measurement we will find that the photon is vertical. In the second measurement, again the photon will end up here and we find that it is vertical. In the third measurement also, and if we just keep on doing, in every measurement we will find that the photon is vertical. So this basically says if we know that the system is in one of the eigenstate, then we can bring in a measurement device in that particular eigenbasis, and then only one measurement is required to reconstruct the state. We just one measurement tells us whether it is vertical or horizontal, and then we just have the state. If it was instead the other eigenket, let's say H, then of course also only one measurement is required, and in that case the photon will go here. Repeating the measurements many times won't yield any different result, and each time it will just go in this in this direction. So if we know that the system is in one of the eigenstate, then only one measurement is required. In fact, the eigenket can be any basis. For example, here the eigenket can be the 45-degree basis. So if we know the system is in this 45-degree basis, 45-degree polarized, then this time in this case we can bring in a measurement device which is in the 45 minus 45, and in that case when we have this photon coming in, it will go this way because that way is the 45-degree polarized and this way would be the minus 45-degree polarized. And so once we see the photon coming in here, we know that it is 45-degree polarized. Repeating this measurement several times over won't yield any different result because each time it has to come out in this direction only. So again, if we know that the system is in one of the eigenstate, we can bring in the measurement device in that particular eigenbasis, and then we can reconstruct the state using a single measurement. But now what about when the system is in superposition state? For example, this is simplest superposition. Psi is superposition of H and V, alpha H, beta V. Now in this case, if we bring in a measurement device and if we do the measurement, maybe the first time when we are doing the measurement, we find the photon to be vertical because photon just goes this way. Second time, maybe the photon goes this way because it has this H component as well. So maybe we just measure H this time. Third time, maybe we measure V, H, V, V, H, V. So different measurements, it's completely now random as to since the superposition state, it is completely random whether we will observe this in this as a vertical photon or horizontal photon. So now infinite number of measurements are actually required to get the values of alpha square and beta square. So that is the state reconstruction. So I mean, in order to reconstruct the state, we need to know alpha and beta. But through these measurements we can actually get alpha square beta square, and again let me just stress that experimentally in order to get this alpha square beta square, we'll have to do a lot of such measurements, and then just by counting how many times we have gotten H and how many times we have gotten V, we can find this alpha square beta square. But this still doesn't yield the phase that is associated with alpha. This just gives the amplitude. And in order to get the phases associated with alpha and beta, one actually has to do interferometric measurements. So if it's a superposition state, one essentially requires infinite number of measurements in order to reconstruct the quantum state. Okay, so now we go to the quantum measurement and state reconstruction for two particle state. So again, just like one particle state, one can do measurement of two particle state. Let's take an example of a two particle state, and here I'm writing the psi as the sum over this two particle state psi I ui. The psi I is the state associated with the first particle, ui's are the states associated with the second particle, and we can write this state psi as this in this form as a superposition. So this state I can be in this first term, where the first particle is psi 1, second particle is u1, and that's the coefficient. It can also be the first particle is psi 2, second particle is psi 2, and the coefficient alpha 2, and so on. So that's a two particle superposition state is what we have over here. Now if we do a measurement on this two particle system, so just like in one particle case, a measurement here collapses the system into one of the states in the superposition. So in one of the psi I ui. So what we have here is just like one particle state, there is a complete uncertainty, intrinsic uncertainty regarding which two photon state or two particle state that this system will collapse into after the measurement. I mean, if you make a measurement here, we may find the system is here, or it's here, or it's here. It is just complete uncertainty. And this is same as we have for the one particle case, but one thing is very clear here is that if the first system collapses into psi I, let's say psi 2, then the second system is guaranteed to be with u2. So the index corresponding to first or second system has to be the same. So of course there's an intrinsic uncertainty as to which two particle state we will find in a given measurement, but if we find that the first particle is psi I, then the second one is guaranteed to be ui. So that is what we get from the structure of the two particle state over here. Okay, so now when we are talking about the measurement in the context of two particle state, we refer to coincidence measurement, because we have to measure both the particles, and that is through coincidence measurement. Now when each particle is in one of its eigenkets, for example, if psi is just h1 h2, so that means first particle is horizontally polarized, second particle is horizontally polarized. That means there is only one term is in this superposition. Now in this case, if you want to reconstruct the state, how many measurements do we need? We just need one measurement. Why? Because this state says the first particle is horizontally polarized, second particle is also horizontally polarized. So if, let's say, if we take the example of parametric down conversion, which produces the two photons, and if first one is horizontally polarized, second one is horizontally polarized, and if we bring in this measurement device in the HV basis, then of course the horizontally polarized photon will go there, and this horizontally polarized photon will go there. Second time if we do the measurement, then of course we'll have the same result. Third time and so on, it will be the same result. So if we know that each particle is in one of the eigenkets, then again only one measurement is enough to reconstruct the two particle state. But when the state is a two particle superposition state, for example, this is the simplest two particle superposition state, that means psi is alpha h1 h2 plus beta v1 v2, that means the first particle is h, second particle is also h, and this state is the first particle is vertically polarized, second particle is also vertically polarized. And here then we will see that just like in one particle case, one has to do really infinite number of measurements to obtain the values of alpha and beta. And of course, to obtain the value of phases of alpha and beta, one has to do interferometric measurements. So this is about the quantum measurement for one particle and two particle. Just one more comment I want to make here is that when we do the quantum mechanics of massive particles, then we work with the operators such as position, momentum, A and B and so on, which is what I have done in this lecture. But when we deal with fields, we do it with the electric field operators, in terms of electric field operators. But whether it is electric field operators or XP operator, the measurement principles and the measurement intuition and the math, it basically remains the same. So here in this lecture I have done it in terms of X and P and not in terms of the electric field operators, but even if we do it in terms of electric field operators, the overall formalism still remains the same. So I will stop here. In the next lecture we will then do EPR paradox, EPR correlation, and in that we will use the concepts that we have developed in this lecture. So let me stop here. Thank you.